So we will just make recording of this lecture. So I will share only my screen. I will not make it full screen. So maybe it will be much better. So maybe this is better solution. Okay. So first we will start with the course contents. We will give introduction to machine learning. And you know, in machine learning, we have supervised learning and unsupervised learning. And of course, you know that unsupervised is more popular than supervised learning. So in fact, unsupervised, maybe it's more important than supervised learning. And supervised learning is important because we have lots of data around us. And it's hard to make those data ready for supervised learning. So it's very, very important to learn techniques from unsupervised learning. And supervised learning also is very, very important because it's there are lots of tools for data pre-processing. It's unsupervised approaches. So unsupervised learning is really very, very important. But it's mainly because there are lots of data around us, and it's hard to really fix those data in a way to use it for training supervised models. So unsupervised learning is very, very important. So in this slide, it's unsupervised learning and the pre-processing. Pre-processing techniques, most of the pre-processing techniques belongs to unsupervised learning. Also, we will talk about representing data and engineering features. This one is very, very important. There are lots of data. Maybe those data are not in the format which is suitable for training, testing, and validating the models. So it's very important to represent those data in a good format and also engineer features. Sometimes we have less number of features. We need to increase those features. Maybe also we have some features. There are some overlaps from features, so we need to find which is more powerful and use those features, and also creating more powerful or superior features. So model evaluation and improvement. So we call it, it's a machine learning pipeline or workflow. It's very important to know it. And it's a very standard. How can we use data for training a model, testing the model, and validating our model? So we need to learn the machine learning pipeline. Feature engineering is very, very important, and dimensionality reduction. Dimensionality reduction, it's like principal component analysis, for example. It's one of the techniques which we really need to pay attention to because it's really very powerful. It will help us, in fact, to find the most important features and to simplify the model. And when we simplify the model, we will be sure that we will try to avoid overfitting and stuff like this. So it's lots of problems later on. So if we can spend some time with our data, we can save lots of time in the training, testing, validations, and so on, and tuning your model. So feature engineering and the dimensionality reduction is very important. And in machine learning, in fact, people know that they should invest at least 60% to 70% of their time with the data. Of course, you will say that, okay, in deep learning, we use raw data. You are correct. But yes, sorry? Hi, Sudan. Yeah. Can we tell at 12 or at 10, for example? Because I have teaching. I will meet him in the break after 1 hour. Yeah. You can just wait here. Yeah. So sorry for this. So feature engineering and the dimensional reduction, very, very important. And after that, we will talk about artificial neural network. Of course, we will talk about a perceptron. The perceptron, it is a basic computing node, or the basic computational node in artificial neural network. It's very, very important to understand the perceptron. And after that, we will connect a number of perceptrons in a way to create an artificial neural network. So we will put it into layers to create an artificial neural network, which will be able to solve a more complex problem. We need to understand also, or to know something about deep neural network. How can we train a deep neural network, convolutional neural network, recurrent neural network, and its applications? And also we need to know something about GPUs and the cloud computing tools. The learning outcomes from our course, we need to have good understanding of the fundamental issues and the challenges of machine learning. We need to learn about data, model selections, model complexity, you know, in artificial, in machine learning, we call it learning from data. So it's very, very important to learn how to deal with data, how to work with big data, which model should I select, for example, model complexity, because it's also, it's a trade-off between overfitting and underfitting. We need also to have an understanding of the strengths and weaknesses of many popular machine learning approaches. So when you are working with your model, at some point you'll say, no, this model will not fit my data, and it's important to find a different approach. We need also to have an understanding of the underlying mathematical relationships within and across machine learning algorithms and paradigms, and the paradigms of supervised and unsupervised learning. And mathematics, it's simple. I mean, the mathematics behind machine learning, it's a very, very simple one. And it's important also to know something about it. I know many people today, they just train machine learning as a black box. Many people, they are very good, they are very clever. So they are very good in programming, in fact, and they use machine learning as a black box, and they use it for solving problems. But also, it's important to know something, what is happening behind the scene. We need to be able to design and implement different machine learning algorithms in a range of real-world applications. I mean, in this course, we will have some home assignments, and in those home assignments, you are just welcome to bring your problem to the classroom. If you have a data set which you want to deal with, we can use this one in the classroom. So you can just bring your own problem, and if you don't have a problem, we will find lots of problems for all people. So it's very, very important to work with real-world applications and real-world data sets. A reading list, there are lots of books, I mean, online and everywhere. So I'm just proposing those. So this book, it's Machine Learning in Action. It has some basic or an introduction about machine learning, I mean, terms and tools, approaches, and so on. Feature engineering, for example, this one, it's a very nice book. It talks about feature engineering and data pre-processing. And also this one, it's about deep learning with Python. So there are lots of books anyway, and I'm updating this one. There are lots of books in 2020 and so on. So the course material, this is the link for the course material. And it's an NTNU link. So it has course contents, learning outcomes, learning methods, home assignments, and exam, right? So it's the website for the course. This year, in fact, I created this GitHub page for the course. So when we are working in the classroom, for example, and when we solve a problem, and when we are happy with it, maybe you will do it, maybe I will do it, anyone else can do it. So we will upload those code into into GitHub. For solving problems, I mean, all time we need data set for solving a problem. So we can get data sets, for example, from Kaggle. This is a website link for it, and also we can get data sets from UCI machine learning repository. So there are many ways to get this. So if you don't have your own problem, if you don't have your own data set, we can download any data set from anywhere and play with it. There are lots of data sets, in fact. Teaching and assessment. Yes. So the teaching, it will be each Monday from 8:15 to 12. We will have a lecture, and each Wednesday from 4:15 until 7, we will have practice with Ming Tao. So Ming Tao, he is a PhD student, and he is working in TEFT lab, and he is working in text understanding in finance. So he has very good experience, in fact. And he started for around 2 years now in his PhD, and he published maybe 2 papers or close to publish 2 papers. He published 1 conference paper, 2 conference papers, and he is so he will be submitting his journal paper, first journal paper soon. So because last year we didn't have those home assignments. Yes, lectures also will be recorded, and we will upload it to Blackboard. So lectures will be recorded and it will be uploaded to Blackboard. So we will have 3 home assignments or mini projects, and in those mini projects, you can work by yourself, or you can create a group and deliver more mature project results. So you can work by yourself. You can just select any small data set and work with it. And or if you want to work in groups, it will be much better, in fact, because in this case, we should expect much mature results. So it will be, for example, you can submit, instead of submitting individual reports, in this case, you can submit a group project report. And finally, we will have an oral exam. And at the end of each lecture, we will try to find some questions. So we can use those questions as a test or as a model for the oral exam. Those are the list of participants. We have participants from International Master Program in Simulation and Visualization. We have participants from International Business and Marketing in Ålesund. We have participants, from Trondheim. We have participants from Computer Science Department, and so on. So in fact, we have some PhD students with us. So in fact, Ahmed is a PhD student. Ahmed Amin, he is a PhD student in economics. We have also Hamad, he is a PhD student in computer science. So for programming, I suggest that we use Colab. We used it last year and it was very fine, but it's up to you. You can just select any tool. This Colab, it's a free and open source environment for Python development, which requires no setups and runs entirely in the cloud. It runs on the cloud, and it's designed for by Google, and it's a suit Jupyter Notebook. So if you prefer to work with Jupyter Notebook in your computer, it's fine. But if you will use Google Colab, you should have better computational resources. And it contains all the pre-installed packages such as Keras, TensorFlow, and PyTorch, which is required for AI and machine learning developers. You can also develop deep learning applications on the GPU for free. It has a GPU, so we need to test this and we need to try this. So I prefer to use it, in fact. And when we have also some project or mini projects, we can just select the best solution or the most simple one, and we can upload it to GitHub, maybe for next year or for other students to just learn from it. So you just need to create a Google account and start using a Colab. It's a very, very simple one. And we have here, so an introduction to Colab. It's online. So we can just stop here for maybe 10-15 minutes. For example, I want you to go to this link and create your account and try to just write a hello world program, for example. So we can just have 10 minutes, for example. It's not a break, but it's just for this introduction to Colab. Just go to this link, please, and try to start writing your hello world simple one. Of course, maybe it's very simple for some of you, but also maybe it's important to be sure that all of us are in the same page. So yes, so can you please? Is it okay so far? You have the PowerPoint. I can share also this link. So I can share this link here, so you can just in the chat. I want to share the link with you, but I don't know how can we. Yeah, this is a chat. So please use this link. Go. Okay, sorry. Maybe I didn't copy it. Yes, please. For groups, it's up to you. I mean, it's up to you and up to the project. So if the project is really very complex, so you can decide. For example, if you want to work with MNIST data sets, I guess maybe 1 or 2, for example, maximum. But if you will go for more complex problems, I guess it would be smart to have a group of people working together. So if you are working with a large data set and it's a really real world problem and it's complex, so in this case, it makes sense to make a larger group. So if you are working in a simple problem, you can just submit individual reports. If you are working in a larger project, you can just make a group. So it's you just select, right? So you cannot, for example, make a group, for example, and just submit a solution for MNIST dataset, for example, or IRIS dataset, for example. It will be really very simple because it's a work of individual. It could be an individual report, but not larger project. So if you want to work in a large problem, text understanding, whatever. So in this case, maybe it will be smart to create a group. So each one in the group he will do apart from the project. Maybe one will be working with the data sets, pre-processing, and the other one will be training models. And maybe someone will be training those models in CPU, and the other will be training those models in a GPU and make comparisons. So, I mean, we are expecting, when you are working in groups, we should expect more complex and more mature work. So I prefer to work in groups, in fact, and I prefer that maybe by the end of the semester, you can write a conference paper, for example. So it will be really very smart to, maybe you can select a project in machine vision and try to find a good project, really, a project. And also are very flexible. So if you want to combine those 3 reports into one, it will be great, right? So you can decide from the beginning. You can make a group, for example, of 2 to 3 persons working together, and you can select a good task, really, which can be published at the end of the semester. So it would be great if we can publish conference paper, for example, by the end of the semester. It would be really very good. So in this case, maybe you need someone to write, you need someone to collect data, you need another one, for example, to work with models, training models, testing, validations, and so on. So in this case, it would be great. So we need at some point to define projects. So, and it's okay also if 2 groups are working in the same project. So at the end, we can make comparison. What is my results compared to your results? What I have achieved compared to the other team? So it will be also fine if 2 teams or 3 teams are working in the same project, and at the end we can make comparison between results. So you can just make groups now, and when you make groups, it's very, very important to be sure that you have all the skills in your group, right? So maybe someone who is really very good in presentation skills and writing skills, someone who is good in coding, right? Maybe someone is good in machine vision and whatever, data collections and so on. So you can just create a group which has all the skills which is required for the project. Because at the end, we need all people in the group to contribute to the project. And in this case, the whole project, we don't have any grades, in fact. So it's also important. We just need you to submit a solution. We don't have any grade for the project, but also we can decide this together. So if you would like to have some grades on the project, which can be used in the final, part from the oral exam, it could be also one way for doing it. So the oral exam, the final grade will be on the oral exam. But if you prefer to, we can decide now if we need really to divide it. We can divide it by the home assignments and the oral exam. So we can put less weight on the oral exam, and we can put more weight on the work during the whole semester. In fact, this option, I like it much better. And maybe at the end of the semester, you will be able to write a conference paper, for example, or a short journal paper and publish it. It will be a really very good production from the course. So please now go to this link and try to, you can continue with the course, no problem. Yeah, of course. So you will attend the course with us because the course. I just have a question from a student, a master student in physics from Trondheim. The course will be digital. So even if we will go to a classroom, we have equipment to stream and we have Zoom equipment, which will make it easy for us to just to stream the course like digital course. But we will have some students in the classroom, right? So, and now you know the list. You have the list of people. You have all emails. If you need pictures and more contact information, the emails, I can provide those information. So you can be part from a team. So you can create a group. You can be part from this group. Maybe one in Oloson, one from Trondheim, maybe one from India, one from China. We have many people abroad, and try to create a group which has the minimum required skills for the project. Maybe one good in programming, maybe one good in defining the problem, because problem definition is really very important. So you are working in physics, for example. So maybe you can define a good problem from your domain, and you try to get a solution using machine learning. So you can define a good problem. You will define it. You will write maybe literature review background and so on. You will plan for the project. You need to get someone who is good in programming, one good, for example, in data collections and so on, machine vision, whatever. So you can create a group, and you can be part from the group, so the group can work together. So you can create a team. You can just meet the group virtually using Zoom link also, and you can work together to develop a solution. So I guess this one will be great. And in this case, if you prefer to put some more weight on the project work, it will be much better, in fact. So we need to reduce, the pressure at the end. When we reach the end of the course, we need people to be happy, and we don't want people to be under pressure and so on. So we can divide the grade between the project work and the oral exam, maybe 50%, 50%, 60% for the project and 40% for the oral exam. So we can decide this together. So you can discuss with the group, and we can decide in which way should we go forward. So now I will leave you with this collab. So please use maybe 10, 15 minutes or 20 minutes, for example. Try to write your Hello World program in collab, right? And after that, so now it's 8:48 or 8:50. We can meet again at maybe 9:05. Is it okay? So we will meet after 15 minutes. So during those 15 minutes, please drink your coffee. I have my coffee here, and try to go to this link in Colab and try to write your Hello World program. So you have get started, data science, machine learning, more resources, machine learning examples. So it has lots of examples, in fact. And you will see that this tool is really it's fantastic tool, and it's easy to use. It make life much easier for us when we need to use packages such as PyTorch, for example, Keras, and so on. So please just go for it, and I will come back after 15 minutes. Thank you very much. Please, you have the slides in Blackboard. You can just download it and start working with this collab and write your Hello World program. And please prepare yourself to share your program with me. So we can just share screen. You can share your screen after 9:05, and we can see. You can just present your Hello World program. Thank you very much.
Want to see the interface, and I spent most of the time figuring out how to upload the files, because I wasn't sure how to get the files from my local computer to Google Colab, because I have worked previously on Jupyter notebooks, and it is rather easy on that to upload files from local computer to the Jupyter notebooks. But in this case, it is sort of a different procedure. So I used some help from Stack Overflow and the document provided by.
Because for uploading data, there are many ways for doing it. You can do it from your local computer. You can do it from maybe Google Drive, for example, OneDrive.
Yeah.
So there are many ways for doing it, in fact. But it's nice to explore and to try to. This is very good. So what do you think? It's a good tool, and it's easy to use. So we can have a single platform, so all people can share together. The code, and we can learn from each other. So thank you very much, Muhammad. Is there anyone else who want to share his screen? Anyone else who want to try? Okay, no more people want to So this tool, in fact, it's very nice. I know. I have, in fact, I'm teaching a course, another course. It's called Intelligent System to bachelor level. But in this bachelor level also, some people, they came from automation. I originally came from automation as well. So people who came from automation, they prefer to work with MATLAB. And also people who came from computer science, they prefer to work with Python. So it's up to you to decide, and if you will create a team for project work, I mean, the team should decide which language people should use. But of course, I recommend you to use Python, because especially in deep learning, it will be much easier. In fact, it will be very easy in deep learning. So I will share my screen, so I can go back to my slides. Okay. So this is the introduction to Colab. You just need to go and try to, play with it. Now we have an exercise. So we have a simple exercise. We have a salary data set. And I will upload those two data sets to Blackboard now. So you can just download it. It's a very simple one. And it's we use it for regression. So in fact, it's the annual salary versus a number of years of experience. So it's a regression problem. So in fact, we have independent variables. The independent variable, it's the number of years of experience. And the dependent variable is the annual salary. And we need to plot, visualize your data set. So you need to upload your data set to Colab and visualize it. And I will upload it now to Blackboard. So I will go to under listening material. We have folder called lectures. I will create another folder and I will call it datasets. I will upload the Excel file. So you can just download this file and you can play with it. So we have, it's called the salary data. I just submitted it, so maybe you can see it now in Blackboard. And also I will have another file, which is Iris dataset. We have Iris dataset, so we call it Iris. So I just uploaded two files to a folder called datasets. So I can share it with you to show you. Okay, stop sharing. I will share something else. So do you see this this folder, datasets? So in this one, we have two datasets, one called salary data and one called Iris. Salary data, it's just two columns. One column is the number of years of experience, and the other one, it's the yearly income. And for Iris dataset, we know Iris dataset. It's 4 features and 1 output, 3 classes. So we will start with the salary data. So please just download this file to your computer, for example, or to your OneDrive. And as Mohammed mentioned last time, he tried to upload a data file into Colab. So now you need to write your code to upload your data file into Colab and try to plot this data. So I can open my Colab. So this is my Colab, in fact, but it's for Iris dataset. So this is the example. So you just need to start by importing those libraries, NumPy, Pandas, Matplot library, and after that you need to upload your data set and plot it. So I will just wait for you to do it. So please just download this simple Excel file. into your computer and try to upload it to Colab. You will have two variables. You have X and Y. Try to plot Y against X or X against Y. So maybe you can take 10 minutes, for example. Is it fine? Ten minutes is okay. Can you get access? Did you download the files into your computer? You can use your mic. Okay, very good. You can use your mic. So just please download those two files in your computer and try to upload it to Colab and just upload it. It's a regression model. I mean, you know the regression model, I mean the equation for the regression model should be it's y equal mx plus c. So if we want to find a line which fits my data, so we need to plot the data scatter plot, for example. So we will plot the data and we want to regress, correct? So we need to predict. So for example, if I have, for example, for number of years of experience, maybe 0 years, 1 year, 2 years, 5 years, and so on. So I want to find what will be my salary if I have been working for 2.5. 2.5 is not in the data, correct? So in this case, we need to find a regression model so we can find all data points in between, and also we can predict for the future. So for example, if my data set it's from 0, for example, to 5. So it's only from 0 to 5. So if I have a regression model, it will be possible to make predictions for if I have been working for 6 years, 7 years, and so on. Correct? So regression model is really it's a very good tool, and it's very simple. If we need to regress a straight line, so the equation of the line will be y equal mx plus c. X it's the independent variable, y is a dependent variable, m is a slope, c is the y-intercept, correct? So the equation y equal mx plus c, it's the equation of the straight line which will fit my data. Y is the annual salary, X will be number of years of experience, M it's the slope, and the C is the intersection with the y-axis. And in fact, to solve this regression problem, we need to find M and C. So first, you need to plot your data set, just visualize it. It's very, very important in machine learning to visualize your data, right? So it will be really very good, very convenient for us, very helpful. So please just, yes, how did you upload the file in Colab? Okay, I will just copy for it. I will copy that part for you and I will share it with you. But I wish if you can search for it, in fact. So if you can search a little bit, just to spend the time. Because it will be more useful, in fact. So it's from google.colab, import files, upload, and you will get the file name. So just use Panda for reading the CSV file. You can print your data, you can print the shape, and after that you can plot your data. So just when someone is ready, he can just share his screen. I will stop sharing my screen. So I can just allow other people to share their screens. So you can just please feel free to share your screen even while you are doing it, and use your mic and discuss. Just imagine that we are sitting in a classroom and people can talk to each other. So please, if you have a solution, just share your screen. There are lots of online sources, by the way, for Python. I mean, I have this book, it's called Python Machine Learning. So all those books are very easy and very, very good. You will learn something. I mean, each book maybe has small part which is really very good. Maybe, and the rest it's just to make it a book, because each one is good in small parts or specific parts. I mean, visualizing the data is very important, because for data pre-processing, if we need to decide what pre-processing techniques should we use, we need to plot our data first, right? And even principal component analysis, sometimes you have data in fifth dimensional space, for example, and we cannot plot it because we cannot plot 5 variables together. So we can use principal component analysis to select 2 or 3, for example, and plot it. So in fact, principal component analysis, it's one way for dimensionality reduction. It's one approach for, I mean, visualizing the data. We simplify the data to be able to visualize it, because visualizing the data is really very, very important. So you can share your screen. Just when you're ready, just if someone is ready, you can just please just say that you're ready. So, okay, Rasmus, he will share his screen. Very good. Yeah, very good. Okay. So please, Rasmus, can you use your mic?
Yeah, sure.
Yes.
Can you hear me?
Yes, I can hear you.
All right. So first, I just copied the code you had already put there to plot the data. Then made a simple program for estimating the coefficients for a linear regression, and then plotted it. Straightforward.
Okay, this is very good. So what are the, can you print the coefficients of the regression line?
Let's see. And B. Does that look about right?
Yeah. Okay, so it looks, but okay. Yeah, because maybe the income, it's by million or something.
I'm not entirely sure.
Yeah, it's times 10 at exponential 6, right? Yeah, so it's they are big numbers. I guess it looks fine.
Yep.
Okay, thank you very much, Rasmus.
Yeah, no problem.
Yeah. So anyone has any question for this part? So regression model, it's I mean the equation, we try to find a straight line which will fit my data. So the regression line will be y equal mx plus c. So the coefficients here will be the slope of the line and the intersection with the y-axis. And in this case, we can use the regression for finding points which does not exist in the data set, because we don't cover all the range. So for example, when Rasmus presented it here, years of experience, maybe it's from 0 to 10, but not all. I mean, not maybe. For example, if you try to find how much income should I get if I have been working for 3.5, for example, maybe 3.5 does not exist in the in the data, so we can use the regression line to find those values. And also, of course, for the future. So if we have the data covering the period from 0 to 10, and I want to find how much income should we take if we have been working for 11 or 12 years, we need to use a regression model to help us to find it. So the equation y equal mx plus c, we will find m, we will find c, and for any x value, we can find the value of y, we can find the income. So maybe Rasmus can share his solution with me, so I can put it in GitHub, if it is okay. Is it okay, Rasmus? Okay, thank you very much. So when we have a good solution, we will just upload this solution to GitHub, so all people can get access to it. So is there anyone else who has a solution who can share it with us? Anyone else who want to share his solution with us? Muhammad, Masoud, Vibio, anyone? Amir? Okay, so in this case, we can go to the next problem. So the first problem here, it's a simple exercise. We have very, very simple data set. We need to upload this data set to our Colab exercise. And we have two variables, one independent variable and one dependent variable. And we need to find a regression model to fit the data. So we can use this regression model for predicting values which does not exist in the data sign. It's like interpolation, for example. So if I have 3 and 4 and I don't have any values in the middle, we can use this line for interpolation. And also we can use this straight line for predicting values for the future. And of course, if you want to evaluate your model, Rasmus, for example, so maybe we need to find prediction error, correct? So we need to divide our data set into a training and testing, correct? So if we need to work correctly, in fact, so now because Rasmus now he find a regression model very quickly, which fits my data set. But maybe we need to test the accuracy of the model. So after having the regression model, we can, maybe for the same data set, we can calculate prediction error. So if someone else has a different solution, we can compare between our solutions, correct? We call it model evaluation. So now you find the straight line, you find the equation of the straight line, you find y equal mx plus c, correct? So we need to make evaluation. How good this model, right? Because someone else, he will find another model. So we will have two straight lines, maybe y1 and y2. So which model is better, correct? So in this case, we need to find prediction error. So maybe the prediction error will be maybe a summation of square difference between predicted and actual, or actual and predicted, or mean absolute error, for example. So it could be mean absolute error or mean square error. So maybe before going forward, maybe you can ask Rasmus to do it. So Rasmus, please, can you make some evaluation for your model? Can you try to find a number to represent how good the model is in predicting annual salary? So maybe you can use mean absolute error or maybe mean square error, or both of them. So in fact, maybe this is a pipeline for machine learning. You have a data set, you try to find a model to fit your data, and after that we need to make some evaluation. So we need to find the prediction error, for example. In the prediction error, there are lots of cost functions which we can use. So maybe Rasmus can try to use mean absolute error and mean square error. So we will go to the next slide, and until Rasmus do it for us. So this is just the solution which I did. It was much simpler than the one which Rasmus did. So just importing those libraries and uploading the file into Colab. You can print the data, print the shape of the data. I divided the data into X and Y, correct? So I have X, which is the independent variable, and Y is the dependent variable. And after that, plotting it. So Rasmus, he created the regression line, correct? And this line, it's Y equal mx plus c. So m, it's the slope of the line, and the c is the intersection with the y-axis. So if we need to make evaluation of this regression model, maybe we can find the prediction error. So the prediction error in this case, maybe you can select mean absolute error and the mean square error. So it's 2 lines. So we need to add 2 lines at the end of Rasmus' program, and we will wait for him to finish it. But until he did it, we will go to the next problem. You have this data set in Blackboard. You just download it on your computer and upload it also to your Colab and try to visualize it. So we have this iris data set. And I downloaded it from this UCI website. And this data set was collected by Fisher in 1936. And the data set has 4 attributes, as you can see here. So we have 4 features, right? So we have 4 features: sepal length and width in centimeters, petal length and width in centimeters. And we have, so this is the feature feature space, for example. So we have 4 features, correct? And this is a target feature. We call it target feature, right? Or classes or output. So we can just call it target feature. So we have input features and we have a target feature. So the target features, it's a classes. We have here 3 classes. So I got some question. Can you please use your mic, please? Because I cannot see this chat. Okay, so anyway, I mean, you have the data set. You have the data set in Blackboard, so just download it and try to visualize it. So of course, it's 4-dimensional space problems because we have 4 features, right? So in this case, we cannot plot it. So you can just select 2, for example, or 3. You can select 2. So just select, for example, sepal length and width, and plot it with different classes. So we have 3 classes in 3 different colors. So just please download the file and just repeat this again. Try to visualize this problem because visualizing it will help us a lot, in fact. So we have 3 classes and they are in order. So iris, setosa, and after that we have iris versicolor and virginica. So we have 3 classes in the target feature. So in the target feature we have 3 classes and we have 4 features. So using those 4 features, we should be able to classify it into one of those 3 classes, right? So please just upload the data to Colab and plot it. And I will stop sharing my screen to see the questions. Okay. I mean to upload. I will share my Colab. I got a question that I mean Amir, he cannot upload his CSV file. So I will just share my my Colab. Please, maybe Rasmus, if you can share your Colab with me, we need to put it in GitHub. So I will share my screen because I did something very simple. Okay. So do you see Amir? Do you see this? Do you see my screen? So I have the salary data set. In fact, when you use Colab, you can add code and text, and it's good for documentations. So in fact, it's important to add text to tell you something about your code, because maybe in the future it will be hard to, if you didn't put comments in your code, it will be hard to understand which part do what, right? So it's really very important. It should be a good habit from the beginning if you can try to mix text with code. So I added this text, which is not executed. It's just a salary data set, which is annual salary versus years of experience. So I just try to explain my data set in a simple way. And I have this code block, import numB, import Panda, and the matplot library. So this one is very important, importing those libraries. And after that, uploading your data. So in fact, my data, it's located in my computer. So I will just no, I will stop this one. Look. I will terminate this one first. So now it's terminated, correct? And it's reconnect. So now, I mean, when you terminate it, in fact, you just clean all those RAM stuff, all information which has been uploaded before. So I will run this part. Now it's fine. Now I will upload my data. So run that part. Choose the file. I stored it somewhere here. So it's a salary data set. Now it's uploading and printing my data. I have 2 columns. The first one, it's years of experience, and the second one, it's annual salary, right? And the data set, it's 30 samples, in fact, 30 or 31 samples, right? So it's 31 times 2, the size of my data set. It's 31 times 2, which means 31 rows times 2 columns. 2 columns because we have 2 features. We call this one, it's input feature, right? Number of years of experience, it's input feature. And the salary, it's a target feature. And we need to find a regression model because you see here, it's a 0, 1.1, 1.3, 1.5. So what if I have been working for 1.4, for example? Correct? So it will be a problem. So it covers years of experience, so from 0 years of experience until 10.5. So, but it's not covering all values. So it's very important to find a regression model. No, data shape, it's just printing the size of my data, right? So, so I will go back to the code here. So I have data equal panda.read CSV file, and this is a CSV file name, correct? So my data, it's uploaded from the Excel file into data or data. So if you print it, it will print the data in this way. Print data.shape, it will print the size of my data file. So my data now, it's a matrix, and this matrix has this size, 31 times 2. So it means 31 examples times 2 features. Okay. So it's printing the shape. If you want to get the length, you just use the word length, L-E-N. After that, I want to divide it into X and Y. So X will be the first column and Y will be the second column. X will be the independent variable and Y will be the dependent variable. So it's just print X and Y again. So it will be printed like this. And also print the shape, length, and so on. And after that, we plot the data. So when we have the the code from Rasmus, I will upload it to GitHub, and I will share GitHub link with all of you, so we can have a backup. So you have some files which we can use for learning. So any question for this one? So Rasmus, did you check? Did you evaluate your model, the accuracy of your model?
Yes, I just finished.
Okay, so just when you are ready, just please inform me so you can just share your screen.
Yep, can you see it?
Okay, and the rest, please just work with the other data set, with the iris data set. Try to visualize it. So just upload it and try to visualize it, similar to this example.
Yeah. Oh,
yeah.
I shared it on Gmail. I sent you
okay.
Sent it to you there, and I made a prediction here for the mean squared error.
Can you share your screen, please?
I think I'm doing that.
Okay. Okay. Yes, I will just take a picture of it. And you added comments. It's very important.
Hmm?
Mm-hmm. Okay, so we have the coefficients b, so it will be x times b plus b0. So it's multiplied by the slope plus intersection with the y-axis. So those are the coefficients. So we have mean squared error. Okay, you used a function for calculating mean squared error, correct?
Yep.
Mm-hmm. So this function, which is mean underscore squared error, this one calculates mean squared error.
Yeah, but you need to import it from sklearn.
Okay, mean squared error.
And it's kind of useful because you can install libraries very easily on Colab with just pip.
Okay. You need to install it.
Only sklearn, or
okay.
I don't know. Maybe it was already installed. I didn't bother checking.
And okay, can you try also mean absolute error?
Mean absolute error. Did I write it right?
Mm-hmm.
Mean absolute error.
Mean absolute Python or SK?
Why is it not the
You didn't report it.
What? Oh, true.
You need to import
You have to import it.
Yeah, sounds about right.
You can just add more line because we need anyway mean squared error also.
Yeah. Mean squared error, absolute error. Let's see. Then here, does that work? Mean absolute error.
Is not defined.
Oh, wait. I have to rerun it.
Okay.
Forgot about that. Let's see. There you go.
So mean squared error.
Yeah.
Okay, but it's absolute error now. Yeah, it's absolute error. So it will return mean absolute error.
Let's see.
So in fact, yeah. So I will share my screen. So it's lecture number 2. It's the course contents. It's introduction to machine learning. We need to learn something about supervised learning and supervised learning and data pre-processing, representing data and engineering features, model evaluation and improvement, dimensionality reduction, perceptron learning rule, artificial neural network, error backpropagation learning algorithm, training deep neural network, convolutional neural network, recurrent neural network, and so forth. So I mean, each week we will go deeply into some of those tasks and try to cover it with some examples. So first, I want to talk about locally or in the cloud. So if you try to build your machine learning model, should you train it locally or should you go to the cloud? We have some cloud services, but it's expensive. We tried it last year and the year before, and we got really very large bill. So you can build, train, and deploy machine learning models quickly. I mean, building and training and deploying machine learning models require massive computational resources. I mean, it's well known, especially if you are working with big data sets. So you will need a fast enough GPU to do deep learning. You need to experiment locally first for sample data. A small part of the data just experiment locally, and then when you are sure that your system works fine, you can go to the cloud. So I don't recommend you to work on the cloud directly. You need to work, I mean, prototyping. You just go for prototyping locally, and after that, when you are working with a larger scale data set, larger scale model, you can go in on the cloud. Because working on the cloud, it costs money. And when it costs money, it's a problem. So you need to be sure that your system is working, your data set is fine, because it will cost money. So I prefer that you go locally first for prototyping, and when you are sure that your model does not have any bugs, it works fine, your data set is okay, you can just go on the cloud and train your model on a larger scale. I recommend you to maybe to buy GPU, for example, GPU laptop with a GPU or a GPU workstation, for example, it's cheap. It's not cheap, but it's cheaper than going into the cloud. As I told you, we tried I mean IBM Watson, I guess, no, Microsoft Azure. We tried Microsoft Azure for 2 years, and we got large bills, very large bill, in fact. So there are also top machine learning services in the cloud, such as Amazon Web Services, Cloud, Google Cloud, IBM Watson, Microsoft Azure, and Alibaba. I mean, those tools, in fact, you can create an account, and you will get some credits. So you can just work for free for short time, and after that you have to pay for it. But also, if you will go for Google Colab, for example, Colab, it has a GPU, and it's on the cloud, and it's for free, right? So we can use Google also Colab, which is a good solution from my point of view. What is the difference between a CPU and a GPU? As you can see here, this CPU, it's multiple cores. It has multiple cores. I mean, those cores, it's arithmetic logic unit, correct? So maybe it has 4 cores, 7 cores, whatever, but it's limited anyway. So the CPU, it's designed for solving simple tasks. But in case of a GPU, which is graphical processing unit, it has hundreds of cores. So it will be really very efficient. So people who has gaming computers, it has a GPU. So I mean, there are lots of laptops with GPUs, and also some GPU workstations. I mean, the workstations, it has an advantage that you can extend, and you can extend it in the future. So for example, you can buy a GPU workstation. For example, you have a workstation, you can have 1 GPU, and in the future, for example, you can buy another GPU, and you can add it to the motherboard, so you can expand it in the future. But if you will buy a laptop, it would be impossible to extend it, right? Maybe you can buy an external GPU and add it to your laptop. So MNIST dataset, it's a very famous one, in fact, right? So MNIST dataset, it's a famous problem. I mean, usually we use those problems for just testing machine learning models. So we will work with problems similar to MNIST dataset. So MNIST dataset is considered as a hello world for deep learning, because we are working with images. And the images, it consists of grayscale images of handwritten digits. And the image size is 28 times 28 pixels. So in fact, it's a 784 pixels. And we have 10 categories from 0 to 9. So it's like hello world in deep learning, and the dataset consists of 60,000 training images plus 10,000 for test. So in total, it's 70,000 images. We divide it into 60,000 for training and 10,000 for testing. And of course, we need to shuffle it, because when you download MNIST dataset, for example, you will see that it's in order, correct? So it will be 0, 1, 2, 3, 4, and so on. So if you will select the first 60,000 images for training, and maybe the rest will be maybe in 9 and maybe 8 and 9. So it's not correct, right? So we need to shuffle the dataset before using it. We need to shuffle it several times to be sure that it's not. It's well shuffled. So all features, all target features are represented, because imagine that the dataset came in order. For example, those are first maybe 5,000-6,000, it will be 0. The next 7,000-8,000, it will be 1, 2, 3, 4, and so on. And if we selected the first part for training the model and testing it with the rest, maybe the rest it will be impossible, because the system didn't see those digits before, right? So training it for digits from 0 to 7 and testing it from 8 to 9, so it will be totally wrong, right? So MNIST dataset, it has been collected in 1980, and it has been used for testing machine learning models and feed-forward neural network and so on. If you want to go for feed-forward neural network, in this case, number of inputs will be 784, which will be huge, correct? So in fact, we can build a model which will train which will train pixel by pixel. I mean, it will work in pixel by pixel. So in this case, each image, which is 28 times 28 pixels, it will be 784 pixels. And we will use those 784 pixels for classifying it into 10 categories, right? 0 to 9. And when you look into those images, it's grayscale or binary, so it's black and white, right? So I mean, the image, in fact, if you look into it, for example, if you look into 0, for example, it's almost black everywhere except some white places. So in fact, most of the pixels does not have any significant information for our problem. Only few set of pixels which has some information, right? So maybe before solving such kind of problem, simply you can just try, for example, PCA, for example, principal component analysis, and try to find a subset of features. I have now, if I will use a raw images, I will have 784 pixels, but maybe you can try to use principal component analysis to find a subset of features which are more relevant to our problem, so we can simplify the problem. So I mean, later on we will work with MNIST dataset, maybe in for feed-forward neural network, and after that maybe our first convolutional neural network, we will use MNIST dataset, and the accuracy here, in fact, it should be around 99% or 100%, right? But of course, you need to use the training set for training your model and the testing set for testing it, and we will see what will be the accuracy for the training, what will be the accuracy for testing, and we will try to identify if we have overfitting or underfitting and so on. The workflow, I mean, there is a workflow, in fact, or a pipeline for, I mean, neural network. So we will feed the neural network with the training data, train image, train labels. The training images, we call it input features, and the train labels. Those labels, we can just call it's a target feature, right? So I have an image for 0, for example, and the label will be 0. I have an image for 1, and the label will be 1, and so on. So the neural network will then learn to associate images and labels. So in fact, the artificial neural network will try to make some association or mapping between inputs and labels. So we have inputs and outputs. So the inputs will be the image, and the output will be the label or the target feature. And we will try to find association between the input image and the label. Finally, we will ask the neural network to produce predictions for test images. So after training, we will use a test set for making predictions, because I want to test if my model can make those associations and can generalize. We need to verify whether those predictions match labels and from the test labels. So we'll just check and verify that those predictions are correct. So in neural network, the core building block of neural network is a layer. So the neural network, in fact, it consists of number of layers. And each layer consists of a number of data processing units or computational units, which we call it a node or a perceptron. So the core building block of a neural network is a layer, a data processing module that you can think of as a filter for data. So in fact, it consists of layers. Why it's in layers? Because when we organize it in layers, it makes it easy for calculations. We can use matrix multiplications. So because in feed-forward neural network, in fact, we go forward, and after that we go backward for adjusting the weights. We go forward for calculating the outputs or make predictions, and after that we calculate the error, and we go backward to adjust the weights. So when the neural network is organized in layers, we make it easy for processing. So we can just, all our calculations can be in matrix notations, right? So just multiply the weights by the inputs to get outputs, right? And apply activation function, of course. So some data goes in and it comes out in a more useful form. Layers extract presentations out of the data, feed into them, hopefully representations that are more meaningful for the problem at hand. So those layers try to find those, extract those representations. Most of deep learning consists of chaining together simple layers. So we connect the layers together. So if I have an input layer, a hidden layer, an output layer, so it's shallow learning, we can call it shallow learning. But when you increase the number of layers, number of hidden layers, when we chain layers together, we can call it deep learning, right? So the difference between deep learning and shallow learning, in shallow learning, maybe we have 1 or 2 hidden layers, but when we have 10 or 15 or 20, for example, in this case, it will be deep learning. And each layer will be responsible of extracting some representations of the data. So we try to simplify, we try to extract some features from the data, in fact. So most of deep learning consists of chaining together simple layers that will implement a form of progressive data distillations. Our network here consists of a sequence of 2 dense layers. I mean, in this simple problems, if we will work with MNIST dataset, we can just say that our neural network will consist of two hidden layers. We call it dense layers. So the second and last layer is a 10-way softmax layer. I mean, the last layer, the output layer, it's the one which will make decisions, correct? So in fact, we have an input layer. The input layer, it's the one which receives input, right? And deliver it to the second layer. Hidden layers will try to extract some representations from my data. And finally, the output layer, it's the one which will make decisions, correct? So if I have 10 classes, for example, in MNIST dataset, so the output layer should give us 10 outputs, correct? If we will use one-hot encoding, correct? So for example, I have the output, the output layer. We have 10 classes, right? So it's from 0, 1, 2, 3 until 9, correct? So using one-hot encoding, so the first output will be, maybe will be 1 and the rest will be zeros, correct? 1 at 0 and the rest will be zeros. So in this, so it will be the probability that the image belongs to this class. We will use softmax layer here. We can use softmax activation function, which means it will return an array of 10 probability scores summing to 1. So the summation of the outputs, it should sum to 1 because it's a probability. So what is the probability that the input image is 0? What is the probability that the input image is 1? What is the probability that the input image is 2? Correct? So we can have it like this, and we can round up to the nearest integer, for example. So we will use softmax, for example. So the output will be probability, correct, which sums to 1. And after that, you can convert those probabilities into integer value, like one-hot encoding. So each score will be probability that the current digit image belongs to one of the 10-digit classes. So, and this figure, it's a softmax, right? Or sigmoid, for example. So this is the activation function. So in this problem, so if you want to implement it, you can download MNIST dataset, upload it to Colab, and try to build your first feed-forward neural network, for example. So in this case, the size of the input image is 28 times 28 pixels, which is 784 pixels, correct? So in this case, I will have 787 or 784. So we will have 784 pixels or inputs. So the first layer will consist of 784 inputs. So the input layer will receive those inputs. It will multiply it by a weight value. We will initialize weights into some random values. We will start with some random values. It will be multiplied by inputs. So the first hidden layer will use those as inputs. We will try to extract some features from those inputs. So we need to select a number of, so the number of inputs will be the number of features, which is 784, if you will use the raw data as it is. You will make those multiplications. You will apply a cost function, an activation function. You will get some inputs, and you will go layer by layer until you reach the output. The output layer will be 10 outputs. We will have 10 outputs. Why 10 outputs? Because the target feature, we have 10 classes. So we just need 10 outputs, correct? The last layer, we call it, it's a decision making. It's the one which makes the decision for us, right? So the hidden layers will try to extract some features, maybe high-level features from the images, and the last layer or the output layer will try to make decision. So when we have an image, of 0, for example, it will try to classify it as 0. When it's 1, it will try to classify it as 1. So the last layer, it is the one which makes the decision. We will use softmax because we need to get probability scores. The probability scores, which is summing to 1. So the summation of all those probabilities will be 1. And this probability will just tell us the probability that the current digit image belongs to one of those 10 classes. To complete the task, so now I have the structure. So from the data set, in fact, from my data set, we can decide the structure of my feed-forward neural network. We will not go into deep learning now. We can just talk about feed-forward neural network. So from the number of features, we can say that I have my data file. So I know that each image is 28 times 28. So in this case, the number of inputs will be 784. And I know that the number of outputs is 10, right? So number of inputs is 784 pixels. Number of outputs is 10, correct? What about the things in the middle? I mean, how many hidden layers? It's up to you to select. How many nodes in each hidden layer? It's up to you to select, correct? So to decide the, it's hyperparameter in fact. So to decide the structure of your feed-forward neural network, we need to know the number of input features. Number of input features is the number of pixels, which will be 784. And number of outputs will be 10 because I have 10 classes. So I have 784 inputs and I have 10 outputs, right? What about in the middle? How many hidden layers? It's up to you to select. Maybe someone will select 1, maybe someone else will select 2, maybe someone else will select 3. So it's up to you to decide, in fact. Just to try, start with 1 and try. If you cannot have with 1 hidden layer, if you don't have good results, you can just increase 1 hidden layer. So you can have 2, for example. Okay, so number of hidden layers, it's hyperparameter, you need to select it. Okay, what about number of nodes in each hidden layer? It's up to you to select, correct? So maybe the first hidden layer, it will have 20. Maybe the second hidden layer, it will be maybe 15, for example. And of course, the output layer is 10. The output layer is 10 because I have 10 classes, right? So in this case, we will have 784 pixels number of inputs, 10 outputs, because the data set consists of this. I have 10 classes and 784 pixels, right? So the number of inputs, number of outputs, it's based on the data file, based on the data set which we have. Number of hidden layers and the number of nodes in each hidden layer, it's up to you to select, right? There is no rule for it, in fact. So you can just try, right? Start with 1 hidden layer, and if the performance is not good enough, you can just add 1 more hidden layer, right? Maybe you can start by 10 nodes in each hidden layer, and if results is not good enough, you can just increase or decrease this number, right? So it's hyperparameter. Hyperparameter means it's a tuning. I mean, we need just to tune it. We need to start with any number, and after that we can tune the model, and we can iterate to find a best combination of those parameters. If you know optimization algorithm, you can use a genetic algorithm to select those, right? So you can just build your code in a genetic algorithm, and the genetic algorithm will try different combinations of those numbers. But how can I know that my model is good or bad? So we need to, after training my model, we need to select a loss function. The loss function, it's the cost function which we need to minimize, right? So I need to train my model, and I need to define a loss function, and it's similar to the one which Rasmus selected, because Rasmus, he selected mean absolute error or mean square error, for example, to evaluate his regression model. I want to see if my regression model is good or bad, right? So in this case, we need to select a loss function. So the loss function will help us to know how the neural network will be able to measure its performance on the training data, and thus how it will be able to steer itself in the right direction. Loss function is very important, right? Because the loss function, we will use the loss function to make evaluation of my model, and also in the same way, it will help me to adjust model parameters. So the loss function, it's very, very important. I mean, Rasmus, when he built his regression model, he selected mean absolute error and the mean squared error, right? So you need to know the difference. What is the difference between mean absolute error and mean squared error? So sometimes some functions, when it's absolute, when it's squared, in fact, it's overestimate small values. It's overestimate maybe large values and underestimate small values, correct? Because the small values will be much smaller and the big values will be much bigger. So you need to know the difference between different. There are lots of, loss functions. So you need to select the one which will give you better results. And also the loss function itself, it's a hyperparameter. So you can just have a list of loss functions and you can test all those loss functions. And at the end, you can select the one which will give you better results. So the loss function, it will give you a measure of how well your model will perform. Because I need to test it. So my model here for MNIST dataset, for example, I selected one hidden layer and I will measure the loss function. And after that, I will add another hidden layer and I will see the difference. Is there any difference? Yes. If adding one hidden layer, one hidden layer improved my performance, in this case, I will keep it. If it didn't help me, I will just ignore it. After selecting the loss function, so the loss function, it's also a hyperparameter, right? So the loss function is a hyperparameter. We need to select an optimizer. And the optimizer, it is a mechanism which will be used for updating the model parameters in a way to minimize the loss function, correct? So this is the optimizer. So in case of feed-forward neural network, we will use, for example, error backpropagation. So error backpropagation, it's a technique which it's a learning algorithm. So error backpropagation, it's a learning algorithm which will be used to adjust weight model parameters in a way to minimize the loss function, correct? So loss function, it's cost function, and all time we try to minimize the cost. So we will use the loss function to measure the performance of the model, and we will use this, this value for adjusting. The optimizer will use this value to adjust model parameters. For example, if the loss function is high, so I need to select model parameters in a way to minimize this value. So we can do this using error backpropagation. We need to use metrics to monitor during training and testing. So we will only care about accuracy, the fraction of the images that we correctly classified. Accuracy. So you can use a loss function, for example, to minimize loss function, and you can use accuracy. For example, if you will use loss function, we will try to go in the direction which will minimize the loss function. And if you will go to accuracy, so in this case, I will try to maximize accuracy. So it could be like in optimization algorithms, they call it cost function or fitness function. When it's a cost function, we try to minimize it. When it's a fitness function, we try to maximize it. So because I try to maximize So it's a fraction of images that will be correctly classified. So after training your model, I trained my model, and I have a validation set, for example, after training. So I will use this validation set for evaluating how the model will perform, the accuracy, how many images correctly classified, and how many images was wrongly classified. So we call it accuracy or loss function. So two quantities are displayed during the training. We have the loss of the network over the training data and the accuracy of the neural network over the training data. We have loss and accuracy. I can have loss and accuracy, correct? So we can try to minimize loss. Usually we use the loss function for, the optimizer will use the loss function, correct? So the accuracy will try to minimize this loss function. And also we will use accuracy to just to describe how good my model is on the training data. So we quickly reach an accuracy of maybe 98.9% on the training data. The test set accuracy turns out to be 97.8%, which is a little bit lower than the training set accuracy. Yes. Okay, so can you ask him to meet me after 12, please? So we need to select a loss function. We need to select optimizer. In Python, all those things are very easy. As I told you at the beginning, some people just do it as a black box. They just bring the code, copy the code and upload their own data sets and just run it. But it's important for us to understand what is going behind. So you will have two accuracies in the training set and in the testing set. We should expect that the accuracy in the testing set will be much lower than that of the training set because I'm training. So for example, you give me this book and I'm just reading and you give me some questions to solve. This is my training. But in the exam, you will give me a set of questions which I didn't see before. So for example, I can study here now. I can read some one chapter, for example, and at the end of the chapter, I have some questions to solve. So my accuracy now, it will be the training because I can go, if I'm not answering you good, I can go to the text, for example, and try to improve my performance. But in the exam, you will have only a set of questions without any training examples. So you will have two accuracies, one accuracy in the training, one accuracy in the test. And those two numbers are very important because those two numbers will give you impression if your model is overfitting or underfitting. So it's very important to identify if you have overfitting or underfitting in your model. How can I see this? We can identify this from those two numbers. So if the accuracy is really very, very good in the training and very, very bad in the testing, it means my system or my model has overfitting problem, correct? Because the performance is really very good for training and they perform very badly with testing. So in this case, I have overfit problem, which means my model just memorize the data set and they cannot generalize and they cannot predict or classify a new data set, right? So those two numbers are very important. So don't be very happy when you have accuracy here for the training, for example. You can get maybe 100% accuracy or 99% accuracy, but you didn't test your system with a new data set. So it will be a problem, correct? Because maybe your model just memorize the training data set. So for example, you build a system for, maybe reading the license plate in the parking, correct? So I collected a data set for training my model and the accuracy was 99%. And then when I deployed it in real life, it cannot, the performance would be really bad. So it will make lots of problems because my model just memorize the few plates which has been used for training it. It memorized it. So I have overfitting problem. So we need to identify if we have overfitting problem because we need to fix it. And overfitting is very dangerous, in fact. Overfitting, very, very dangerous. So the gap between training accuracy and test accuracy is an example of overfitting. The fact is that machine learning model tended to perform worse on new data than on their training data. So those numbers, we need to compare those numbers and we need to identify if we have overfitting problem. We will do this again and again by examples, and so don't worry about this. And we will learn techniques how to avoid overfitting, how to fix these problems. Deep learning, I found it in a book. Maybe it's not maybe a very good example, but it's geometric interpretation of deep learning. So, but I can just skip this one because we will not talk about deep learning at the moment. We will go back to deep learning later on. So topics to be covered today, we need forms of machine learning, formal evaluation for machine learning models. How can we evaluate machine learning model? We need to prepare our data for machine learning, feature engineering. What is feature engineering? I mean, just at the moment, we need to understand what is feature engineering, but later on we will take some examples. And also overfitting, how can we identify that our model is suffering from overfitting and how can we solve it? And as I told you, you need to keep tracking the accuracy in training and testing. From the accuracy in training and testing, you can identify if you have overfitting problem or not, or underfitting, correct? But underfitting, it's okay, it's something good, but overfitting, it's something really very dangerous, which we need to deal with. And what is the universal workflow for approaching machine learning problems? We have a workflow, we have a pipeline. We need to know this universal workflow or pipeline because all people just follow the same pipeline or workflow. We have, the material from those for today. I got it from this Fundamentals of Deep Learning, chapter 4. from this book, and also feature engineering for machine learning from this book. I mean, each time we will try also to mention the sources, so you can go back onto it and try to go deeply into those stuff. So types of machine learning problems. We have different types of machine learning problems. We can start with binary classification. Binary classification, it's supervised learning. So it's just black and white, yes and no, for example. Dog and the cat, for example. So I have a set of images for dogs and the cats. There is also a data set called the dogs and the cats. So we have images, and we need to classify it. Is it dog or cat? So it's black and white, yes or no, correct? So it's a binary classification problem. So it's a supervised learning. Since the training data set is labeled, we have labeled the data set, or the data set is labeled, or we have target features. So the target features, it's the labels. And the classification task where each input sample has only two classes, 1, 0, or yes and no. Some examples include, for example, credit card fraud detection. We need to see if we are under fraud detection. Medical diagnosis. Sometimes we want to say, okay, if you are working with cancer data set, for example, is it cancer or not? So it's yes and no. And spam detections, dogs and the cats data set. There are lots of data sets, in fact, which is binary classification. Binary classification, it's lots of data set, and it's a very important set of problems. Those binary classifications. So binary classifications, so the output, it could be 0 and 1, in fact. So we can have only one output. So maybe the output will be probability, right? So we can use softmax activation function, because the output will be a number between 0 and 1. And later on, you can just round this number to the nearest integer. So you can convert it into 0 and 1. Or you can convert it into one-hot encoding. So maybe I have a set of images. So the first image, it's for cat. So, and it's labeled that this one is cat. The second image, it's for dog, and it's labeled dog, right? So I can just convert cats and dogs into zeros and ones. I can convert it into binary classification problem, or I can use one-hot encoding. And in case of one-hot encoding, I will convert this one into a vector of 2 elements. So now I have, I mean, it's like iris data set, for example. I have 3 classes. So the 3 classes, so the target feature, it's 1 column, and maybe this column it will be, I can change it into 0, 1, and 2, for example. So 0 will be 1 class, 1 will be another class, 2 will be a third class, because we have 3 classes. In case of dogs and the cats, we can convert it into 0 and 1, right? One-hot encoding. So when it's a cat, it will be 0. When it's dog, it will be 1. Yeah. Any questions? The second problem, it's multi-class classification. In the multi-class classification, the classification task where each input sample should be categorized into more than 2 categories or classes. And this is very important because, for example, if you go to AlexNet, for example, they use a data set where we try to identify object in the image. So it's a multi-class. So each image has multi-classes. So maybe we try to find how many classes in the image. Maybe an image has a cup, maybe an image has a TV, has a computer, has a keyboard, or all of those in the same image, right? So we call it multi-class classification. So an example is, let's say, classify a set of images of fruits, which may be orange, apple, and pears, for example. Classify handwritten digits, for example, correct? So each image has multi-class. So multi-class classification is very, very important. And there are lots of work in unsupervised learning in this one, in multi-class classifications. So multi-class, we have multiple classes, right? So each input sample should be categorized into more than 2 categories or classes, right? So I have an image, and this image, for example, has orange and apple. So I need to say that, okay, this one has orange and apple at the same time. Maybe some images has only orange, some has only apple, but also some images has orange and apples at the same time. So it has multi-classes. Multi-label classifications. Multi-label classification is a classification task here where each input sample can be assigned multiple labels. For instance, a given image may contain both a cat and a dog, and should be annotated both with cat label and the dog label. So the number of labels per image is usually variable. So it's like Alex dataset, for example. And finally, scalar regression. Scalar regression is a problem which Rasmus has solved today. So it's a task where the target is a continuous scalar. For example, predicting house price. I need to predict the house price. So maybe we have also this house price data set, for example. So you have you have the area, you have number of rooms, you have location, area per square meters, for example. So you have many features, and using those features, we try to predict the house price, right? And the idea here that maybe we have a house which has features that does not exist in not one of those examples. So I need to predict its price, for example. And also the example for today for the annual income for number of years of experience. I have the data set, and the data set covers years of experience from 0 to 10, for example, 10 years. But not all years of experience are covered. So we need to predict if I'm working for 5 years and a half, how will be my salary? So in this case, we can use this one we can use a regression problem. We can solve the machine learning problem as a regression problem. So we will get the straight line, which is y equal mx plus c, and we will use this one to regress, to predict what will be my salary after 2 years working here, what will be my salary after 2 years and a half, and so on. So we can just say that in general machine learning problems, it's a classification and regression problems. And in classifications, we have binary classifications, we have multi-class and multi-label classification problems. There are 4 branches of machine learning. So we have supervised learning, we have unsupervised learning, we have self-supervised learning, and we have reinforcement learning. So it's a different of learning. In case of supervised learning, it's the most common use, in fact, and it consists of learning to map input data to known targets. So we have a target feature. So we have some input features, and we have target features, and we try to find this mapping between inputs and outputs. We can use this one, when it's supervised, so we can use it for classifications and regression. In classifications, we have this MNIST dataset, dogs and the cats dataset, for example. So it's a classification and it's supervised. For regression, it's similar to the problem which we used today, or for example, house price dataset. So the house price dataset, we have a set of input features, and we have the target features. The target feature will be the price. So for each specification, for each combinations of inputs, we have a house price, different house price. So we can use it for classifications, and we can use it for regression. Of course, for regression, we must have a target feature. The target feature here, it will be the annual income, for example, or it will be the house price. It must be supervised, right? So we can use it for classifications, and we can use it for regression. Unsupervised, it's a branch of machine learning which consists of finding interesting transformations of the input data without the help of any target. We don't have any target feature. And we use it for data visualization, for data compression, data denoising, or to better understand the correlations presented in the data set at hand. So this is very, very important. So for example, imagine we have MNIST dataset, and we will just ignore the target features. So we will use only images, right? And we will use unsupervised approach. So we know, because we visualized the data, and we know that we have 10 features, 10 target features, 10 classes. So in this case, in fact, you need to decide how many classes we have, right? So if you will select 10 classes, maybe the data by itself, it will be classified into 10 classes. One class called 0, one class called 1, one class, but you need to label it because we don't have labels. So in fact, this MNIST dataset, for example, we can solve it as a supervised learning, and we can solve it as unsupervised learning. When it's supervised learning, we have the target feature. So we will use those target features to solve the problem. We will train the model to classify each image into a target class. But in case of unsupervised, we have input images, we have features, input features, but we don't have labels. We don't have target feature. So in this case, we can solve this problem if we will ignore the last column, if we will ignore labels. So in this case, we will solve the problem as unsupervised, right? And in this case, we will cluster it, right? We will cluster it into, we will solve it into 10 clusters. We need to select number of clusters, right? We need to select number of clusters. So for example, when we visualize the data, we can see, okay, I can see that there are 10 clusters. We need some knowledge. We need to know some domain knowledge, right? So maybe some expert, he will say, okay, I know that MNIST data set, it's about 110 digits, and it should be classified into 10. So we can cluster it into 10 classes. But we need someone, after solving the problem, we need someone to give labels to each cluster, right? So he will go to the 0, he will say, okay, this one looks 0, this one will be 0, I will call it 0. I will call this one 1, 2, 3, 4, 5, 6, 7, 8, 9. So after solving the problem into 10 clusters, we need someone to give a label to each cluster. And after that, when you have some new data in the future, because we need to deploy it in real life, for example, I have some new image coming in the future, maybe it's 7, for example, so it will be automatically classified into 7, right? So maybe we will find, if we will use nearest neighborhood, for example, so we will just find the distance between the center of the cluster and the new data set. We will find that, okay, 7, this image, it's closer to cluster called 7, right? We can have overlap between 7 and 1, correct? Sometimes, because when you see the confusion matrix in MNIST data set, you will see that all neural network make some confusion, maybe between 8, 9, 0, and maybe 7 and 1, right? So we will have some confusion. So maybe if someone writes 7 and I want to classify it, I will send it to my neural network. So the neural network will, or the algorithm will try to find the distance between 7 and the 10 classes which we have. So maybe it would be closer to 7, or maybe 7 and 1, correct? But it will not be close to 9 because it's different. It will not be close to 8 because it's different. So it will be closer maybe to 7 and 1. So maybe closer to 7 more than 1, right? So in this case, we can say, okay, now we can deploy it in real life and use it. So unsupervised learning is very, very important technique. Why? Because there are lots of data everywhere and we don't have time to label it, right? So sometimes you have data set, you collect a data set, blood analysis and CRT images and MRI images and so on, but no one really has time to do it for you because you need to build a machine learning to help doctors to, for example, to classify tissues in a knee, for example, right? So you have lots of MRI images and X-ray images and so on, but there is no one has time to do this for you, correct? So in this case, we can just use unsupervised learning. You have huge data set. You can use an unsupervised learning technique and it will classify it into a number of classes, but he can just say, okay, usually we are interested in 10 tissues here, correct? So I know from the doctors that they are interested into classifying it into 10 tissues. So I just know this piece of information. So in unsupervised learning, I need to decide how many tissues, how many clusters. And after training my model, I will just go to the doctors. So I will tell him, okay, now I have 10 clusters. He will look into it and he will give a label to each one in 1 minute. So in this case, it helps us to save lots of time and effort. But if you will go for supervised learning, no, in this case, for each image, I need to look into it and I need to give a label to it. And imagine that if it's multi-class, for example, each image has maybe 12 or 14 tissues. So it will take too much time to label it, right? So one way to avoid this is to use unsupervised learning. Self-supervised learning. Self-supervised learning is supervised learning without human annotated labels. In self-supervised, so it's a supervised, but without human annotated labels. We don't have labels. You can think of it as supervised learning without any human in the loop. So there are still labels involved, but they are generated from the input data, typically using heuristic algorithm. So as I told you, in supervised, for example, we need someone to look into the images and try to classify it, to give a label. So in MNIST data set, he will look into 0. Okay, this one looks 0. This one looks 7. This one looks 3. This one looks 2. It takes time, but we have a human in the loop who will help us to annotate images and give labels. Dogs and the cats, for example, so we need a domain expert. He will look into the image and they say, okay, this one dog, this one cat, this one dog, this one cat. So he will help us to annotate and annotate those images. But if we don't have, so we can use this self-supervised learning. And in self-supervised learning, we need to find a heuristic approach. We need to find an algorithm which will help us to annotate images automatically. For example, predicting the next frame in a video given past frames, or the next word in a text given previous word. So we need to find an algorithm to help us to make those annotations. And finally, reinforcement learning. Reinforcement learning, it's a very, very important branch of machine learning where there is an agent, and this agent receives information about its environment and learn to choose actions that will maximize some reward. So in fact, we have an agent, and this agent, he has some actions which he can decide to do some actions. For example, I have a robot, and this robot, he will collect input from the environment. So for example, he has a laser range scanner, for example, a laser sensor, and the laser sensor collects information about the environment. And he will decide if he should go forward or turn left and right or backward, correct? It's like the small robot which cuts the grass, for example. It just moves in one direction, correct? And then when something in front of it, it will just collect information about the environment. And if there is an obstacle in front of it, maybe it will go back, right, one step, and it will turn left or right. So it's an algorithm, right? And maybe the reward here, it will be to minimize hitting stuff, for example, or just, so we need to have some reward function, which we need to maximize. So this is reinforcement learning. So we can build a reinforcement model to train how to perform in this way. For instance, a neural network is that looks at a video game screen and outputs the game actions. Maybe I have a game and I have some game actions. Those game actions may be forward, left, right, backward, for example. And we have a function a reward function, which we need to maximize. So we need to select maybe those reward function and maybe to maximize the score, for example. And we will use this reinforcement learning approach to train our neural network to perform better. So we call it reinforcement learning. After building my model, it's very important to evaluate your model. So the idea, I have a data set, we learn from data, we selected a model, but I need really to be sure that this model is correct. So we need to evaluate, after training my model, I need to evaluate this model. We evaluate the model using brand new data for testing it, and this data, we call it never before seen data. So in fact, when we start working, when you collect your data, you need to divide your data into a training set and a testing set, correct? Training set, we will use it for training my model, and a test set we will use it for evaluating my model, correct? It's important because it will give me an indication of overfitting. Overfitting is really very dangerous in machine learning, because I remember many years before, people just train models, and when they have good results, they just are happy with it, but they don't know that the model is not working. In fact, it's just memorizing some data points, but it cannot generalize. It cannot make good regressions. It cannot make good classifications. So it's very, very important to hold out part from the data for testing, so I can test my model using a brand new data set. In the training, we adjust weights. We adjust model parameters, number of learnable parameters. So we have hyperparameters and we have model parameters. Model parameters, it's the learnable parameters, the weights which we need to adjust. And the model parameters, we adjust it in the training phase. So in the training phase, we adjust model parameters. And as I mentioned, if you have a larger data set, if you have a big data set really, you can divide it into a training set, a validation set, and a test set. So in validation, we tune model configurations, we tune model hyperparameters. Model hyperparameters, it's maybe number of hidden layers, number of nodes in each hidden layer, correct? And so on, so how can we do this? We can do this using a validation set. So the validation set, in fact, is used to evaluate the fine-tuned model. So imagine I have 20 samples, 20 examples. My data set consists of 20 lines, 20 images. So I will have 10 for training, maybe 5 for validation, 5 for testing, correct? In the training, of course, remember to shuffle all time. Remember to shuffle your data set. Because if I have 2 sets, for example, if I have 2 classes, 0 class and 1 class, for example, it's binary problem. So maybe it's in order. So maybe the first 10 will be 0 class. The last 10 will be 1 class. So if I selected the first 10 for training and the next 10 for validation and testing, it will be a problem. I will test a model with 1 class which has not been trained on before. So it will be a problem. So my numbers will not be reflecting, reality. So it's very important to shuffle. You need to shuffle your data set very well. And after that, divide it into a training set, a validation set, and a test set. I will use the training, which is the first 10 points, for training my model. So I will decide a structure of my model. I will decide a set of hyperparameters. For example, I will start with 1 hidden layer. And in the hidden layer, I have 10 nodes, for example, and I will train my model, right? So I need to test the accuracy. So I will use the validation set to test the accuracy of those. So the validation set, in fact, it's the test set for the training set, correct? So I will test the accuracy using those validation set. I will test the accuracy. And after that, what will happen? I will try to fine-tune the model. So maybe I will try to adjust some threshold values, maybe the activation function, hyperparameters, any hyperparameters. Train the model one more time and test, correct? And when we are happy with the hyperparameters, we will go for the test set. We will use the test set to just to check if to evaluate the final model. So finally, I have a final model. So after training and validations, I will have a final model, and I will use the test set to evaluate the final model using the test set. So I will have 2 accuracy. Maybe I will have an accuracy from validation and test, or just the training and the test. I will use those 2 numbers to check if my model has overfit problem or not. So in testing, we measure the generalization power of your model to avoid overfitting and maximize generalization, in fact. Test set is used to evaluate the final model. Repeatedly tuning and adjusting the model hyperparameter using the model performance on the validation cause information leak. Sometimes we have this kind of information leak, and the information leak is some information from the validation set leaks into the model, right? Especially if you will shuffle it all time. So at some point, you will use some of the validation, or maybe some repetitions, some of the examples which has been used for training will be used for validation. So we call it information leak. So the model began to overfit if trained and validated using the same set. Of course. So if you will train and validate the model using the same data set, the model will start to overfit. It will start to memorize my data points. We have a technique which is called sample holdout validation. Sample holdout validation. Sample holdout validations, we have a data set. We will divide this data set into 2 sections or 2 subsets. 1 set for training, 1 set for testing. So set apart some fraction of your data as your test set. Train on the remaining data and evaluate on the test set. To prevent information leaks, you shouldn't tune your model based on the test set. You cannot tune your model using test sets, right? Because if you will tune your model using test set, so the model will know something about it. And in the testing phase, you will have some results which is not correct because the model has seen those data points before. For the test set, it should be brand new data set. It should be brand new data set for testing. But if you will divide your data set into one for training and one for testing, and if you will validate your model or if you will fine tune your model using test set, you will have this kind of information leak, correct? So maybe you will overestimate the performance of your model, correct? So if I will train my model using the training set, and if I will use the test set for fine tuning my model, I will have this kind of information leak. So you should not tune your model based on the test set, and therefore you should also reserve a validation set. So it's highly recommended to reserve a validation set from the training set. So you need to divide from the beginning. You need to divide your data into training, validation, and testing. The validation set will be used to fine tune your model, right? So in this case, we will avoid information leak. If little data is available, then your validation and the test set may contain too few examples to be statistically representative of the data at hand. And this is easy to recognize if different random shuffling rounds of the data before splitting end up yielding very different measures of model performance, then you are having this issue. And in this case, we need to use k-fold cross validation and the iterated k-fold validation. So, we shuffle the data all time. So we can iterate, for example, I can shuffle, divide the data into training set and testing set, and testing my model. If you repeat this process several times, and if you feel that there is big difference between results each time, so in this case, it means your data is really very small, and and you have, very few samples which are representative of your data. In this case, we will have a problem. We will have this information leak, and we need to use other techniques. Other techniques, it's k-fold cross validation and the iterated k-fold cross validations. This is very, very important. In k-fold cross validation, do you want to take a break? Please, if you want to take a break, just let me know. So we have around 50 minutes left, so I can continue, and or if you want to take 5 minutes or 10 minutes break, just inform me, please. Can you say something, please? Do you want to take 5 minutes break or 10 minutes break? If not, I can just continue. Okay, so someone he said we can take 10 minutes, and someone he said we can just continue. Yes, can you just please maybe one more? If you are voting for it, we just need one answer, one more, because one said we can take 10 minutes and one said okay, we can have a break, so we can just have 10 minutes break. Yeah, we will have 10 minutes break, and we will start at 11:20. We will start again at 11:20. Okay, so we can start again. Today it's more about concepts and stuff like this, but maybe the next week it will be more practical. But also, so I will share my screen again. So also we will talk later on, in details about those techniques, and we will implement it step by step. And of course, implementation in Python is very, very simple. So k-fold cross validation. What is k-fold cross validation? So if you have a large data set, if you have a big enough data set, we can divide it into training set, validation set, and testing set. But what will be the situation if really it's expensive to collect data and I have a small set of data and it's impossible to divide it into, it's impossible to hold out a set for testing, for example. So in this case, we need to use k-fold cross validation. And in k-fold cross validation, it's an approach which is used for model checking, not training, in fact. So in k-fold cross validation, we divide the data into k partitions of equal size. So maybe k equals 3 or k equal 5. In this example, for example, we have 3 folds. So in fact, we selected k equals 3. So we divide the data into 3 equal folds. For each partition, we will train a model on the remaining k-1 partitions. So if you select k equals 3, for example, first, of course, we need to shuffle the data set. And when we shuffle the data set, after shuffling the data set, we will divide it into k sections or k partitions of equal size. And we will train the model for each partition. We will train the model for k-1 partitions. Correct? So for k equal 1, we will train the model for 2 partitions and test it for partition number 1. So it's 2 for training, 1 for testing, right? Or validations. We don't care. I mean, validation or testing, it doesn't matter because here we just use it for. So we will train the model for k-1 folders or partitions and the test for the third one. And we will repeat this process 3 times. Each time we start by brand new model. So I have my model, I have my data set, and I designed the structure of the model. I know how many hidden layers, how many nodes in each hidden layer, and so on. So I will start with my model. I will initialize my model parameters by random, and I will train the model for those 2 sections and test it for this section. And from this test, I will have a validation score. I have a loss function, or I have prediction. I will measure accuracy. So I will train the model for those 2 sections, and I will test the model for the last section, for section number I, and I will repeat this process 3 times. So at the end, but in the second time, I will start with a brand new model here, and for k equals 3, I will start for a brand new model here. So each time we start by a brand new model. Brand new model means it's the same structure, the same number of hidden layers, the same number of nodes, but you just initialize your model parameters by random. Randomly initialize your model parameters. So I will start by brand new model here, and I will have a validation score from this one. And I have a second validation score here. So validation score number 1, validation score number 2, validation score number 3. So now I trained the 3 models, correct? I selected k equals 3, and I trained the 3 models, and I have a validation score 1, validation score number 2, and validation score number 3. So the final score will be the average of those 3. So it will be this one plus this one plus this one divided by 3. So now I have a validation score or a test score, correct? And after that, what will happen? After that, I will just initialize a new model. After having this score, I will initialize a brand new model, and I will use the whole data set for training it. So in this case, we have a score because I try to find validation. I want to find accuracy. So this one will be the minimum accuracy. Why it's a minimum accuracy? Because in fact, in reality, I trained the model using the whole data set. So we use this approach for model checking. So I will use this one for calculating this average score. And after having your average score, you will initialize the model, your model again, randomly, and you will use the whole data set for training the model. So we should expect that the final model will perform much better than each of those 3 models. So it will be much better. Why it's much better? Because I used the whole data set for training it. We didn't have any holdout set for testing, right? So we used the whole data set for training. I use this whole data set for training the model, and at the same time I have this final score, average score, which is the minimum accuracy. Why it's minimum accuracy? Because in each K here, I train the model using 2/3 of the data, but in fact the final model which we will deploy has been trained using the whole set of data. So in this case, we can avoid this hold-out approach. So K-fold cross validation, it's important technique, and it's very, very important, especially when you have a small data set. Sometimes it's very expensive to collect data. So for example, we have been working in a project where we collect those MRI images for knees, for example, and we have only 12 data sets. We have only 12 data sets. So it's impossible to just hold out 4 or 3, for example, for testing, and use 7 or 8 for training, because it's expensive to collect those data sets. Why it's expensive? Because we ask people to voluntarily go to the X-ray or MRI scan and take a scan of their knees, for example, and after that, we ask some domain expert to cluster it into some number of tissues, for example. So it's expensive. It takes time, in fact, to collect this data set, and it's impossible to just hold out a set for testing. So in this case, we can just use K-fold cross validation. If you select K equal 5, what will happen? We will train 5 models, right? And each model, we will have 5 validation values or test values, for example. We will use the average score by taking the average values of those 5 models. And after that, we will train a brand new model with the whole data set, and that is it. So K-fold cross validation is really very, very important. We will implement it also in many examples later on. There is something called iterated K-fold cross validation with shuffling. So with shuffling, this is very important, because I mean here, for example, if we selected K equal 3, we will have 3 models. But in fact, in iterated, you can just repeat this process several times, and each time you will shuffle. So I can just select K equal 3, and in each time I will repeat it 5 times. Correct? So in this case, I will have 3 times 5. So I will have 3 times 5, 15 validation score. And in this case, you will get the final average score also. So it will be more representative of the model accuracy. So when we repeat this process several times, we will get more representative numbers. Why? Because if your data set is really very small like this one, and I divided it into 3 partitions, maybe it will be biased. Maybe some data will not be representative, correct? Because, for example, if we have 3 classes and I have 10 points, for example, maybe by chance, right? In the validation set, it will be testing class number 3, and the class number 3 will not shown here in the training set, right? Because the number of data points is really very small. So in this case, it should be, we need to get balanced data set, and it's impossible. So one way for solving it is to just repeat this process several times, and each time shuffle your data. So we will use iterated K-fold validation with shuffling. So this one for situations in which you have relatively little data available, and you need to evaluate your model as more accurate as possible. It consists of applying a K-fold cross validations multiple times, shuffling the data each time before splitting it into K-folds. The final score is the average of the scores obtained at each run of K-fold validations. You end up training your model by B times K, right? B, it's the time of iterations, times K, which is the number of folds, where B is the number of iterations you use, which can be very, of course, it's expensive approach, because doing this process several times, it takes time and computational resources. But of course, you will get more representative numbers. So K-fold cross validations and iterated K-fold cross validations, you can just try it, for example, with MNIST dataset. So maybe next week, for example, when we are working with MNIST dataset, we will try to build a feed-forward neural network. We need to test K-fold cross. We need to start, for example, by hold-out validations, K-fold validations, and iterated K-fold cross validations. And we need to find what is the difference. Is there any difference? And so on. We have some important notes. It's randomly shuffle your data before splitting it into training and test sets. if the samples are ordered by their class to be sure that both your training and test set are representative of the data. It's very, very important. And as an example, it's IRIS dataset and MNIST dataset. So if you go to IRIS dataset, you used it already in the example. I'm waiting, by the way, I mean, some of you to send me his solution. So in IRIS dataset, it's a 150, I guess, data points. The first 50, it's one class. The next 50, it's a second class. And the last 50, it's the third class. So if we didn't shuffle your data set, and I just splitting my data into training and testing, so I can just say, I will take the first 80% for training and the last 20% for testing. Without shuffling, it will be a problem because I will be testing the model against class number 3 and not class number 1 and not class number 2. So maybe the accuracy will be 0%. Correct? Maybe it's not 0%, maybe 20%, because some of the third class will be already in the training data set, right? So it will be a problem. So it's very important when the data is in order to shuffle your data set. Shuffle it several times to be sure that all classes are represented. So if we didn't shuffle the data set, we will not be sure that my data set is not all classes are represented in the training data set and the test data set. You can also do it. For example, you have MNIST data set or IRIS data set. Try to divide it now and try to shuffle it one time and see if you really have, if all classes are represented in the training, validation, and testing data sets. If you are trying to predict the future given the best, for example, a time series, for example, if I have a time series, it's a problem because time series, it's in order, right? So if you are trying to predict the future given the past, for example, tomorrow weather, stock movement, and so on, you should not randomly shuffle your data before splitting it. You should always make sure that all data in your test set is posterior to the data in the training set. Time series prediction is time series. When it's time series, it would be a mistake if you will shuffle it, right? If you want to shuffle it, we need to divide it first, and after that we can shuffle it within each set. We need also to avoid redundancy in your data. If some data points in your data appear twice, it's happening in real world applications, in fact. So I'm collecting data, and because I have some sensors collecting, some cameras, and so on, so sometimes I will have a data set which is repeated, right? So then shuffling the data and splitting it into training set and validation set will result in redundancy between training and validation set. You will be testing on part of your training data, which is the worst thing you can do. Make sure your training set and validation set are disjoined. This is a problem. So I have a line which is repeated, and I'm shuffling, and I just divided into a training and testing, and by chance, those two lines, one become in training and one become in testing. So it will make a problem for me, because the model has been trained on this example and will be tested with this example again. So my numbers will not reflect, reality, correct? So this is a problem. So we need to avoid redundancy in your data set. So as I told you, it's very, very important to spend time checking your data set before starting building your model. Redundancy is a problem. Redundancy is a problem. And now I'm not talking about features. I'm talking about rows. Because my data set, it will be as a matrix, correct? Number of rows will be number of examples or data points. A number of columns will be features. So maybe the first few columns will be input features, and the last few columns will be target features. It will be also a problem if I have repetitions in features. So maybe imagine I will call it maybe, for example, we try to predict maybe income based on number of years of experience, educations, male and female gender, correct, and so on. So maybe some repetitions will happen here in the features. Maybe educations and the number of years of experience, maybe there will be some redundancy here, correct? Or birth date and the number of years of experience, maybe it will carry the same information. So if you have repetitions or redundancy in features column, we can use principal component analysis to remove those redundancy. correct? We can use principal component analysis. But if you have repetitions in rows, each row means a data point. If you have repetition in rows, we don't have any algorithm for doing it. You need to check it by yourself and try to identify it and remove this redundancy. So you need to spend really time with your data set to fix it. So if I have collecting images of cats and dogs, and I have 2 images of the same dog, for example, right? So it's a redundancy. So in this case, maybe if I split my data into training and testing, one data point will go to the training, one data point will go for testing. So in fact, I'm testing for the same point which has been used for training. So numbers will not reflect reality. It will overestimate the performance of my model. My model will not be good as we can see, right? Because it will overestimate the performance of your model. So we need to avoid redundancy. So it's a very important redundancy in terms of column and rows. Column, it's feature, and rows, it's data point. Important questions before model development. We need, how do you prepare the input data and the targets before feeding them into a neural network? We need to use data pre-processing, right? Data pre-processing is very important because I want to be sure that my data are in the correct format, standardized, normalized, and so on. And the feature engineering. Feature engineering, it's very important. Feature engineering, it's talking about, it's about column. Maybe I have 10 features, but there are some overlap between features. So I need to find this unique features to train my model. So maybe you can use principal component analysis to just select the most important feature, right? Maybe you can use correlation coefficient between features, so we can remove redundancy, because maybe 2 features have carry the same amount of information. So I don't use both of them. I just need to use a single one. So can you just use this correlation coefficient between features and the targets, correct? And if I have high correlation between 2 features, if it is positive or negative, correct? It doesn't matter, in fact. So if I have high correlation between 2 features, in this case, I need to use, maybe I just need to use one, not both of them, because both of them have the same kind, carry the same kind of information carry the same kind of information. So it will be repetition. So instead of using 2 features, I just need to use a single one, because both of them has high correlation, and there is high correlation between those 2 features, and both of them carry the same information. So I need to use a single one. Feature engineering also, maybe I have feature 1 and feature 2, but maybe you can create a feature 3 using those 2 features, right? The new feature, it could be linear combination of those 2 features. So maybe x1 times x2 will be more useful than x1 and x2, correct? So you have a model, and the input to this model, it's x1 and x2, right? 2 features, and I will train my model. Maybe x1 and x2 by itself, it's not useful. Maybe it's better to just use x1, and the second input will be x1, x2. Maybe it will be linearly separable if we can use a kind of feature engineering, because some problems like XOR problem, for example, it's linearly non-separable, right? Linearly non-separable. And if you want to classify it, you need to use a complex feed-forward neural network to solve it, because it's linearly non-separable. Maybe if we can spend some time on feature engineering, we can find a set of features which will help us to make it linearly separable, and just solve it using a perceptron. Just solve it by a decision line, but by a straight line, right? So when we spend time on feature engineering, maybe you can create new features which are more representative of the knowledge in my data set. And also feature learning. Feature learning, it means creating new features. So I will start with data pre-processing for neural network. Data pre-processing aims at making the raw data at hand more amenable to neural network. This includes the vectorization, normalization, handling missing values, and feature extraction. So in data pre-processing, we need to talk about data vectorization, value normalization, and handling missing values. Missing values is a problem. So we need to check, I need to display my data point. I need to put it in a table and display it on the screen to see if we have some missing values. Of course, we have some packages in Python which fix this for us. But it's very, very important to take care of missing values and handle it. So if we have a pipeline for machine learning or workflow, we need to know the locations of the place of the feature engineering in the machine learning workflow. So good features make the subsequent modeling step easy and the resulting model more capable of completing the desired task. It's very, very important. If you use relevant features, you will just go ahead into your solution directly, and you will get a model really which is just target that desired task. Bad features may require much more complicated model to achieve the same level of performance. I have bad features, so it will take more time from my model to achieve the same results, right? And it's the same, for example, if there is a crime somewhere, and they just, the police go around and they try to ask people about main features of a criminal, right? So maybe some people just go straight forward to the main features, and they will describe those main features which can help us to capture him, for example. So it will help the police to capture and to stop the crime quickly, because the criminal, he is around, and they just ask people about main features. So if you can give precise and accurate features, maybe it will help them to capture the criminal quickly. But maybe another witness, for example, he was just to give lots of data and lots of information which is not relevant, and it will take more effort from the police, for example, to capture the criminal. So it's the same way. If you have good features, it will help the model to achieve good performance quickly. If you have bad features, maybe it requires more complicated model and more training time and more data to reach the same level of performance. So we have some raw data, and the raw data we collect it from some sources. For example, maybe some sensors, some cameras, all the books, newspaper, and so on. So we have some sources of data. We collect our raw data here, and we need to clean and transform those raw data and extract useful feature from it. And after we have good features, we can just use those features for modeling and building a model, right? And after that, we can deploy and test this model. Data vectorization. All input and the targets in a neural network must be converted into vectors of floating point data or integers. So we need to put it in numerical value. So sometimes I collect images, and on those images we have some target classes, for example, or target features. Maybe in the image I have orange, apple, and banana, for example. So I cannot just say it's apple and banana and orange. In fact, I need to convert it into a numerical value. So I have feature. Those features we need to convert it into its categorical variable, and this categorical variable we need to give it a value, right? So we need to give it a number. So we need to convert those into numbers. It could be a floating point. It could be, for example, 0.0, this one 0.5, this one will be 1, for example. It could be integers, 1, 2, 3, for example. It could be one hot encoding, right? So you can just represent each orange, because I have 3 classes. So you can just represent this orange by 1, 0, 0, the apple by 0, 1, 0, and banana, for example, by 0, 0, 1. So we call it binarization or one hot encoding, correct? So this is my data set. So maybe it's a model for predicting the price of items, for example. So I have those features. Maybe it's orange, apple, banana, and the price it's 5, maybe 5 krona, 7 krona, 3 krona, for example, per kilo or per stick. So now I need to train a model to predict the price, right? So in this case, I cannot, my machine learning model will not be able to understand orange, apple, banana. I need to convert it into a numerical number, because as I told you, the input to the feed-forward neural network will be numbers, and those numbers will be used in the forward direction or forward path to calculate the outputs. So I cannot work with text, we cannot work with images, we need to convert it into numbers. So hot encoder is used to perform binarization of the category and include it as a feature to train the model. So in this case, I will just convert it into numbers using one hot encoding, for example. label encoding, for example, like this one, and convert all those categorical variable into numerical value. So my model can understand it. Value normalization, it's a problem. So sometimes, for example, you have a data set which predicts income, for example, and it has, for example, educations. So if you have maybe a PhD degree, it will be 1. If you have a master degree, it will be maybe 2, for example. If you have bachelor degree, it will be 3. So we convert those categorical variable education into numerical value. We have, for example, years of experience. Maybe it's maybe 1 year, 2 years, until maybe 10 years, for example. So it's a big range, in fact. So from maybe 0 to 10 years. Maybe age. Maybe I have people who started their job at 20 and some people who just joined us at age of maybe 65 or 60, for example. So we have a very wide range, right? Income, for example, we try to predict income. So maybe income will start maybe from 500,000, maybe to 20 million per year, for example, imagine. So it's a very wide range, in fact. So in fact, it's a problem because all feature values have a very wide range. So if I try to use those numbers with my machine learning models, some features will be very, very small numbers, between 0 and 1, for example, and some features will be very big numbers, right? Between maybe 500,000 to 20 million, for example. So the range is really very, very big. And at the same time, also, I have inputs, which is binary. Gender, for example, male and female, correct? 0 and 1. So the scale and the range of inputs, the features, it's different, and it will make a problem for my machine learning models. Why it will make a problem? It will make a problem because we have activation function, right? So in fact, we have inputs, and if this range of input is different, some very high big numbers, some very, very small numbers, we will multiply those numbers by the weight values. So it will be converted, it will be transferred into some numbers. Those numbers also, it will be the same. Numbers are very high, and some other numbers are very small. And we need to apply it to the activation function. And when we draw the activation function, in fact, maybe if it is sigmoid, so the output should be number between 0 and 1, correct? So maybe all very large numbers will be converted into 1. Not only large numbers, maybe all large numbers greater than 1 to 10 millions, it will be converted into 1. So in fact, we squash a big range of numbers into 1, right? So when you draw the activation function, unfortunately, we don't have a blackboard, but when you draw the activation function, you will see that all large numbers which are greater than 1, it will be converted into 1. So we squash lots of information into 1, in fact, and which means we lose lots of information. Because when we talk about income, so the one who is taking maybe 10 krona, so if you draw the activation function, sigmoid activation function, you can see, and we are talking about income. So all information, if we talk about income, for example, so people who are taking 10 krona up to 10 million krona per hour, for example, or per year, for example, all those information will be converted into 1, which means we lose information, we lose knowledge. So I have a feature, which is income, and all those numbers are converted into 1. We don't have any variations. So I will just show you here. So I will draw this activation function. Do you see this activation function? So we have this activation function. So in fact, in this case here, all numbers which are greater than 1 converted into 1, because this is 1, correct? This one, maybe it's -1, and this one +1, right? So in fact, all numbers which are greater than 1 are converted into 1. So if we are talking about a feature, an input feature, which is income, and all people who has income greater than 1 krona until maybe 10 million krona, all those informations are squashed into 1, converted into 1, which means we lose information, in fact, right? We lose information. So it's very important to normalize. If we normalize our data set, so if my feature vector, I have a feature vector, and if we normalize all values between 0 and 1, it will be located here, right? We will have lots of variation here. So we will be able to differentiate between one who has 100,000 per year and one who 10 million per year, for example, there will be some difference. The one who is getting less, he will be located here, for example, and the one who is getting more, he will be located here. So we will have variations. So without normalization, without data normalization, I mean, data normalization means we normalize each feature to have a mean. We have several types of normalization. So I will talk about min max scaling, for example. So in max scaling, it takes small values. Most values should be between 0 and 1 range. So I have all income of the people, and I will scale it into the range between 0 and 1. And when it's between 0 and 1, now it makes sense for my activation function, in fact. So when it's between 0 and 1, it has, so we keep variations. We keep variability in my data set, in my feature. I just converted people who are getting 10 million, it would be 1. People who are getting 100,000, maybe it will be 0.1, and in between all other values. So in fact, all peoples are represented here, right? So we keep variations in my data set. I keep all those informations. But if we didn't scale, if we didn't use min max scale, we will lose the whole information. We will lose it. So we will have an input to my neural network, which is income, but in fact, it does not carry any knowledge. It does not carry any information for my model. So min max scaling is really very, very important. Be homogeneous. All features should take values in roughly the same range. So we try to put all values in the same range, right? It's homogeneous, meaning all features. So now, when I use the min max scaling, I fixed the income. Maybe I have, so now it's between 0 and 1. And at the same time, I have gender, which is 0 and 1. So it's between 0 and 1, so we are okay. If we're talking about educations, for example, maybe educations, it's or years of experience, it's a number between 0 and 10 years, for example. So we need also to min max scale it to be in the same range between 0 and 1. So just divide it by 10. So we divide it by the range. So min max scale, we just divide it, we subtract minimum, and we divide it by the range. So we are sure that it's between 0 and 1, right? So this is the equation for min max scaling. So it's x minus minimum of x divided by the range of x. So in this case, we are sure that all features are between 0 and 1. When all features are between 0 and 1, we will deal with them equally, in fact. So my neural network will deal with them equally. But if you have one between 0 and 1, and one between 0 and 10 millions, so maybe in this case, my neural network by itself, it will try to classify, right? So it will select which one is important, which one is not important. It will pay attention to some of those features, and it will ignore the rest. So if I didn't normalize all features to be in the same range and to be homogeneous, maybe at some point it will be selective, correct? So it will give more weight to some features and it will ignore other weights. Maybe it will pay attention to income and it will ignore other things, right? So I want to get a loan from the bank, for example, and I provide all years of experience, I provide income and so on. So maybe it will be biased towards income, for example. So if my income is this, I will get a loan regardless of my education, my years of experience, and so on, right? So we need to build a model which will deal with all features at the same level. How can we do this? By adjusting all features and be sure that all features are in the same scale, in the same range. Another approach, it's called normalization. It's a variance scaling. So we have min-max scaling. We have something also called variance scaling, and it's about normal distribution. We try to put all variables in the same normal distribution. So we normalize each feature independently to have a mean of 0, and normalize each feature independently to have a standard deviation of 1. So we try to give all, we need to force all features or transform each features into to have 0 mean and 1 standard deviation. So we have mean max scaling and variance scaling. Also, if you are working in a project, you can try both of them. You first try mean max scaling, and you will see the performance, and you can try to use, for example, variance scaling and to see what is the difference. of course, we need to use model evaluation. I need to evaluate. And at the end, you'll have a table, right? In the case of mean max scaling, mean absolute error was this one, mean square error was this one. In case of variance scaling, mean absolute error was this one, and the mean square error was this one. So we'll have a table, and from the table at the end, you can just say, okay, I guess for this data set, it's much better to use variance scaling and not mean max scaling, because variance scaling, it gives me much better performance. So in fact, you need to try all different combinations and have a table, and from the table, you will select the approach which you should apply. This is min max. We have 4 minutes left. Min max scaling, it will be like this one. Feature scaling and the normalization is usually done individually to each feature. We do it feature by feature. Min max scaling squeezes or stretches all feature values to be within a range of 0 to 1, right? So all my data points, it's in a big range, and I try to put it in a range between 0 and 1. So the minimum one will be 0, the maximum one will be 1, and the rest will be between 0 and 1. So it could squeeze, right? And imagine if it is very, very small numbers, it's the same. So if my features are very, very small numbers, multiplied by 10 to minus something, right? So it's a very small values. So we can also stretch it to be between 0 and 1. So we need to squeeze or to stretch all feature values to be within the range of 0 to 1. And this is the equation. It's a very simple one. So in your collab, for example, you can just try it with years of experience and income, right? You plotted the data. You have, the salary data set. You have all values. They are not in the same range. So try to normalize it, for example, and plot it, and see the difference. Is there any difference? Is it more useful? And so on. So maybe we'll end today with this slide, standardization or variance scaling. In case of variance scaling, it subtracts off the mean of the feature over all the data point and it divides by the variance. So the resulting scaled feature has a mean of 0 and a variance of 1. So this is the original data set. We try to normalize it. So we will subtract each data point from the mean. First, we will calculate the mean for my data point, for my feature. So for my feature, we will calculate the mean and we will calculate the standard deviation. We will subtract each x from its mean and divide it by the variance. Right? Standard deviation to get all data normalized. Right? So all data will have a mean 0 and a standard deviation of 1. I guess we will stop here today, and next time we will continue, and we will continue with more examples. But as I told you, this lecture today, it will take time. It's 54 slides, and we cover the main topics, some main topics which are very important. But later on, we will go in details for each one in examples. So we will try to implement some examples, and we will try to implement a different approach and see the impact, right? So thank you very much for joining me today, and please let me know if you have any feedback for today. Share your code with me, and let us meet next time. And I will upload examples. So examples which I got from Rasmus today, I will share it in Blackboard. And also the video for today's lecture, I will upload it to Blackboard. So thank you very much for joining me today, and please let me know if you have any questions.
Professor, I have a question from
Yes.
the K-fold validation slide.
Which slide?
K-fold validation.
K-fold validation, yes.
Yeah. In that you said that we are going to train the data on the entire data set and then evaluate it, making it into K different partitions, in which one will be for validation and the two others will be for training. I'm confused in that, because if we have already trained the data on the entire data set, how can we retrain it on the two different partitions?
Yes, in fact, in K-fold cross validation, I have a small data set, so I cannot divide it into a set for training and a set for testing. So to avoid this, because data are expensive, so we can select k, for example, equal 3, for example. So I will divide the whole data set into 3 partitions, right?
Right.
And those 3 partitions, I will train the model with 2 partitions and test with the third one.
Okay, the 2 partitions will be combined
No,
for
it's
training.
not. No, I mean in the code, it's not combined. In fact, you can just divide it into 3 partitions, and combine it in the training, right?
Okay, right.
Just to combine it in the training, and you will evaluate the model for the third one, and you will go for k equal 1. You do it in a while loop, for example, and for k equal 2, you repeat this process, but you need to reinitialize your model weights with new set of random weights, correct? So it's a new model, and you will train it with a different 2 and test it with the third one, and so on. You repeat this one 3 times, and each time you will calculate the accuracy. So from the first time you will have accuracy 1, for example, accuracy 2, accuracy 3. Take the average, so it will be the average accuracy of your model. Now I have accuracy of my model, right? So now we are done with k-fold cross validation. And after that, you will reinitialize your model with a new set of weights and train it this time with the 3 folds, right? So in this case, you will have a model which has been trained using the whole data set, and at the same time, you have an average accuracy of your model. We don't need to test it anymore, correct? Because it has been tested already.
Right. Thank you, sir.
Mm-hmm. So k-fold cross validation is very, very important. In fact, when we have a small set of data, or it's expensive to collect data, and it's expensive to just hold out a set for testing. So in this case, we really need to use the whole data for training my model. How can we do this? Using a k-fold cross validation. Yeah. Any other questions? Any other questions? Okay, so I mean, we will close now. And please, just if you have any questions, just contact me anytime, and I will answer you as soon as possible. And we will meet again next time, next week in the same time. I guess we will not have, exercise session this Wednesday, because maybe we don't have too much. Maybe it will not be each week to have those exercise stuff, but we will have lecture each week. So maybe next week we will have exercise part when we start doing more things which need more coding. But please share your code with me, and if you have any questions, just contact me anytime. And thank you very much for today.
Goodbye.
Thank you very much. Bye-bye.